For multivariable case, now we have calculated for fx. So if x is independent variable, then there is a function over x is fx. If fx is function over x, then y equal to fx. If y equal to fx, then variation in y that is seen along the variation in a vector u. So if there is a unit variation along the vector u, then what is the variation along y, where y is a function over x, that is fx. So y equal to x square. This is what we have been seeing. Now, what is dy by du? dy by du, what is dy by dx? dy by dx is variation, number of units that we see changes in y when there is one unit of change that we see along x-axis. So that is dy by dx. So era of dy by dx is over. Now the new era has come, that is dy by du. So variation that is seen in along y direction when there is a unit variation along any vector u. If it is I, u is I, then it is dy by dx. Otherwise, it is dy by du. So, if it is dy by du, then we saw that it is dy by dx into dx by du. So, dy by dx, so if y equal to 2x, y equal to x square, then dy by dx is 2x. 2x into dx by du. So dx by du is nothing but if u is a vector, then it's unit vector. So I consider it as a unit vector. So if u is a unit vector, then u's component along x-axis, that is dx by du. So dy by du is dy by dx into dx by du. Okay. Now if we take for multivariable two independent variable x and y, then fxy, earlier dy by du, now fxy. Earlier it was dfx by du, now dfxy by du. Okay, so how much we see variation in function over x and y? We can say z also. So function over x and y, how much function over x and y means how much z, dz by du. How much function over fx, function over x and y, how many unit it changes if there is one unit of change along unit vector u. Okay, so if this is x-axis, this is y-axis, then dy by dx is how much unit of y changes if there is a delta x along the x-axis. So 1 point, 1 point, 2 point, 2 point along x-axis. So if I take first point, what is x? Second point, what is x? Difference between these two is delta x. At these 2 points, what is y? If one y is here and one y is here, okay, or I am taking this as y-axis and this is x-axis, suppose. Then at one point y is here and at one point y is here. So what is difference in y with difference in delta? So delta y by delta x. So for one unit of change along x-axis delta x, how many unit of change that we see in y? That is dy by dx. Now this is any vector u. How much y is changing for any displacement, that is delta u? No, it is not delta x. Any vector u, along this vector u, if there is a displacement delta u, then what is delta y by delta u? What is variation that is seen in y when there is a delta u variation along the vector u? dy by du. Okay, in one corner case u can be x, then it will be, so in one special case u can be x, then it is dy by dx. Otherwise in generalized form it is dy by du. Now we are calculating dfxy. Now we have two independent variables. Earlier we calculated dfx by du. Now we are calculating dfxy by du. So if it is x-axis and it is y-axis, this is xy plane, then this is any vector u. If this is any vector u, then there are 2 points. One point what is fxy and other point what is fxy. Then we have to get the difference in fxy at these 2 points divided by delta u, that the length we have taken, dfxy by du. How many fxy would change if there is variation of delta u unit along the vector u? That is the question. Now, as per the so as per the new invented rule, chain rule, if I want a variation in any of the functions, so if a function has two independent variables x and y, so suppose that at this point it is fxy xy, this is fxy plus delta u, this is fxy, this is fxy plus delta u. So what is fxy plus delta u? What is fxy? So minus. So fxy plus delta u is nothing but fx plus delta ux. So delta u is x component, y plus delta uy, and then minus fxy by delta u. So at any point AB, it is f a plus delta ux, b plus delta uy minus fab by delta u. So this is what we want to calculate. Now that era is over. How much we will put our brain in pressure? So dfx by du equal to dfx along x-axis. So if we are calculating for two independent variables, fxy, x and y, then if we are calculating the variation dfxy, means variation that is seen in fxy. So first we will calculate for component x, then component y, dfxy by du plus dfxy by du. First dfxy along x-axis plus dfxy along y-axis. So dfxy by du equal to dfx by du along x-axis plus dfx by du along y-axis. So in both component we have to calculate dfxy by du. If it is along x-axis, then y is constant. If it is along y-axis, then x is constant. dfx by du, where y is constant along x-axis, plus dfx by du along y-axis when x is constant. Let's see what I am doing. Now, suppose this is x-axis, this is y-axis, this is dfxy. So if that is the case, then if that is the case, then this is u vector. If this is u vector, then this is first point and this is second point. This is AB and this is AB plus delta u. That is A plus delta ux, B plus delta uy, x component and y component of the delta u. Now, at any point AB, I want to calculate the z, how much z it is. Okay. So if I want to, if there is a difference here, okay, so we are calculating FAB and then A plus delta ux, B plus delta uy. So these are the 2 points. Now, if I want to calculate if there is a variation of delta u, then how much z would vary? So z, if I want to calculate the z, okay, so let's forget this delta u. Or if this is delta u, then it has x component and it has y component. Now at any point AB, okay, at any point AB, delta x, if I shift, then I see there is how much change in z. Then from this, okay, so this is the point, okay, from this is the u vector. At this point AB, I move along x-axis, not along u. I move along x-axis and see if it is delta u exchange, then how much z would vary. If that is the case, I calculate this variation in z. Now from AB, I move along delta y and see how much z would vary. If I add both, then I calculate how much z would vary if there is a delta u variation. So this is, we will slowly move to local linearity. We will prove through local linearity. But this is the chain rule. If I want dfxy by du, then dfx by du along x-axis when y is constant, plus dfx by du along y-axis when x is constant. We don't have third component, otherwise plus third component. So all the components we have in F. So earlier we did dfx by du, that is dfx by dx, dx by du, because we have only one component x. Now we have two components x and y. So dfx by du along x-axis y constant plus dfx by du along y-axis when x is constant. Okay, so now dfx by du equal to dfx by du along x-axis plus dfx by du along y-axis. So dfx by du along x-axis, then dfx by dx into dx by du plus dfx by dy into dy by du. So dfxy by du, variation seen in fxy when there is a unit variation change along u vector is dfx by du equal to dfx by dx into dx by du plus dfx by dy by du. Okay, this is amazing equation. Dfx by dx into dx by du plus dfx by dy into dy by du. Two things are multiplied and then added. This gives signs of dot product. If I have a vector A and B, what is dot product of A and B? A B cos theta or AX BX plus AY BY. Here dfx by dx is one component of a vector plus dfx by dy, that is another component of a vector. Dx by du, one component of a vector, dy by du, another component of a vector. So we are calculating variation that is seen in dfxy for multivariable when there is a delta u variation along the vector u. That is dfxy by du. We are calculating that is variation seen along x-axis by du plus variation seen along y-axis by du. That is dfx by du plus dfxy by du. That is dfx by dx into dx by du plus dfx by dy into dy by du. So dfx by dx by dy, these are two component of a vector, and dx by du and dy by du are two component of another vector. So dx by du and dy by du are two component of unit vector u, whereas dfx by dx and dfx by dy are two vector of a new vector that is coming, that is called gradient vector. See the chain rule, how simple it is. If I want dfxy by du, then dfxy along first component, that is x by du plus dfxy along another component y by du. So if there is a point AB and at this point we want the variation in z when there is a variation along x-axis is delta x and variation along y-axis is delta y, then we have to find the variation along x-axis whatever it is, then variation along y-axis whatever it is, then we have to add it. This is how we can get the variation in d. This is how we get delta fxy. If you want delta fxy when there is a variation of delta x and delta y along x-axis and y-axis, then delta fxy is y equal to delta fxy along x-axis plus delta fxy along y-axis. If we add both, then we get delta fxy. This is normal rule. So we are calculating correctly. Anyway, we will proceed. So now we have two vector. One vector is u vector. One is called gradient vector. dfxy by dx, dfxy by dy. These are two x and y component of a gradient vector, whereas dx by du and dy by du are two vector of two component of u of unit vector u. Means if u is not a unit vector, we will calculate the unit vector. And for that unit vector, these are the two components dx by du and dy by du, where dfx by dx and dfxy by dy are two components of a vector called gradient vector. Okay, so now what is fxy? We started with y equal to x square. Let make it a equation in 2D. So y equal to x square means x square minus y equal to 0. I can make it a x square minus y equal to a constant. If that is true, then fxy is x square minus y. If it is x square minus y, then dfxy by dx is 2x, where y is constant, whereas dfxy by dy is minus 1, 2x and minus 1. So gradient vector is 2xi plus minus 1j, 2xi minus j. Okay, so gradient vector is, so if I take any value alpha, then 2 alpha I plus at point A B, then 2 ai minus j. So this is the gradient vector. 2 at any point AB, then 2ai minus j is the gradient vector. Okay, so if I take a kind of any value, so a as 4, then a as 4, then it will become 8i minus j. Okay, so can we see if I keep growing it? Okay, so it would change anyway. So it is like if it is 100, then 200i minus j. So I component is increasing rapidly where j component is same. This proves that it is getting flatter, flatter, flatter. So if it is I equal to 1, then I minus j. So if it x-axis, this is y-axis, okay, or if it x-axis and this is y-axis, then it is like this 45 degree, I minus j. But as we grow, then x grows in 2 times. If x equal to 10, then it is 20 I minus j. Then it is almost flat to x-axis. If it is 100 to 100 I minus j. So gradient, if y, if we have equation x square minus y, then gradient vector is 2x, okay, one side dfx by dx, and dfx by dy is minus 1. So it is 2 2xi minus j, or if it is at point AB, then it is 2ai minus j. Okay, so this is the equation of gradient vector. Let's suppose that we did kind of through chain rule. So dfx by du equal to dfx by du along x-axis, dfx by du along y-axis. So dfx by dx into dx by du plus dfx by dy into dy by du. So dfx by du and dfx by dx and dfx by du are the two component of gradient vector, whereas dx by du and dy by du are two component of unit vector along the vector u. So dfx by dx is nothing but partial derivative along x-axis, and dfx by dy is partial derivative along y-axis. If these two partial derivatives if you form in a vector, this is called gradient vector. So for equation we start with y minus x square. So if I take y around on that other side, so if you keep both, then it will be x square minus y. Then it is 2x minus 1. 2x is the dfx by dx and minus 1 is the dfx by dy. So 2ai minus j is the gradient vector. If we see the local linearity where we have we have dfxy, we have dfxy in terms of dfxy. If we have a function fxy, then dfxy is nothing but it is a kind of uh, it's a kind of, it is considered as how much there is it. So dfx fxy equal to fxy is an equation. Okay, so if fxy is an equation, then tangent or local linearity at any point AB, The equation of that is, okay, so there is a graph that has equation fxy. Now at any point a, b, if we want tangent surface to be calculated, then there will, say it is gxy. So tangent surface is gxy, then gxy would be gxx fxxy, the partial derivative along x-axis. So gxy, the new surface tangential equation will be fxxy into x plus fy xy into y. So new the tangential surface equation as per the local linearity is fx xy, so that is partial derivative along x-axis into x plus partial derivative along y, that is fy xy into y. So what is delta gxy? If this is the equation of gxy, then what is delta g? What is change in gxy? If there is change in x as delta x and there is change in y as delta y, so delta gxy would be fx xy delta x plus fy xy delta y. Okay, so now if I divide it by delta u, then delta gxy by delta u equal to fxy into delta x by du plus fyxy into dy delta y by delta u. So it comes to same thing. If I take local linearity where gxy is the tangential surface, that is fxy partial derivative x-axis. Okay, so gxy equal to fxy into x plus fyxy into y. If I calculate the delta gxy, then it will come at fxy delta x plus fyxy delta y. So if there is a displacement of delta x along x-axis and displacement along y is delta y, then how much gxy would change? If tangential surface of a equation, that is fxy at any point AB is gxy, then gxy equal to fxxy x plus fyxy into y. So if there is a, at that point AB, if there is a displacement of delta x and delta y along x and y axis, then how much gx would change? So delta gxy is fxy delta x plus fyxy delta y. Now if I divide it by delta u, then it will become delta gxy delta u equal to fxxy delta x by delta u plus fyxy delta y by delta u. Same thing what we are calculating, that dfx by du, this is what we are saying, equal to fxxy or dfxy by dx into dx by du plus dfxy by dy into dy by du. So now it comes to gradient vector, and we calculated that dfx by x and dfx by y are two components of gradient vector, whereas dx by du and dy by du are two components of unit vector along u vector direction. So we start discussion with what is the fxy, what is the change in fxy, what is dfxy, change in fxy when along the any unit vector u, so dfx by du. So it came as a dot product of two vectors, one is gradient vector and one is unit vector u. So gradient vector is dfx by dx along x-axis and dfx by dy. These are the two components. If equation is y equal to x square, then I can make equation as x square minus y. Then 2ai minus j at point AB is the gradient vector. Okay, what is the if this is the gradient vector, then where gradient vector lies? Okay, okay, so now we have calculated the gradient vector. So gradient vector is at any point AB 2ai minus j. Okay, now gradient vector dot u, gradient vector dot unit vector along u vector. If I this if these two dot we do, then we get variation of fxy along vector u. Okay, if that is the case, then suppose that u is tangential circle. If u is x-axis, okay, so along any vector u, then if u is x-axis, then we have then use y component is 0. So the use second part, that is the gradient vector dot, we say gradient vector dot u. So use second part uy is 0. So only first part would remain here. That is dfx and fxxy, or dfx by dx, and dx by du is 1. So dfx by dx. So along, if I take a unit u as x-axis, then this is partial derivative along x-axis. If I take it as y-axis, then first part is gone. Then it remains a dfx by dy into dy by du. So dy by du is unit vector, that is j. Then dfx by dy, that is the partial derivative of y-axis. Now, suppose that u is along the tangential line. If y equal to x square, y equal to x square is like this, then at any point AB it is a tangent. So what if u is tangent? Then how dfx by du would vary? If that is the case, then again, so we have, as per the principle, if I want a calculation of any function's derivative, any function derivative along any vector u, then it is dfx by du. That is gradient vector dot u. So gradient vector is 2I minus j. What is u? U is tangential vector. What is tangential vector? So tangential vector is nothing but y equal to mx, where m is the derivation, that m is the slope of the line at any point AB, that is dy by dx. So if I say y equal to dy by dx at any point into x, that is equation of the of the tangent.